Check, check.
Yeah, is this on? I guess so. Anyway. Can the Zoom people hear me?
Yes.
Started. So we're very happy to have Aninda Sinha from ICTS beginning today's education. He will talk to us about the quantum life effect.
Okay, thank you very much. Thank you very much for the invitation and also for coming for the seminar. I'm going to talk about the quantum life of pi and just one small clarification. So I have a joint affiliation as this slide suggests. So I thought I am going to start by showing you some pictures of both places, because if you look at the globe, Calgary and Bangalore are North Pole and South Pole in some configuration. So the time difference is also 11 and a half hours or 12 and a half hours, depending on what it is. So this is ISC, roughly speaking, what you would see right now. Although I must say that I've never seen roads of this kind. So I wonder when these pictures were actually taken, but this is ISC. I don't think this is AI. I think this is some picture, yeah. And so this is the open day. So this is open day last year, or I went with my daughter. This year I missed it because I was in Canada. And there were 60,000 people last year. I don't know the count this year. And so I wanted to actually taunt the people in Canada by showing them that, you know, this is so beautiful. And in Calgary, the weather is like this. I mean, it was actually quite nice. So this is the Bow River, and it was full of snow. Perimeter was much worse than this. But anyhow, so I wanted to tell you about some history about pi, because that will form a key player in my talk. Although the motivation is going to be string theory, but the one of the things in mind you can keep in mind is pi, and it'll be a driving motivation for much of my talk. So this is, yeah, I wonder why you didn't have it in the Madhava hall. I mean, yeah. Yeah. Anyway, so this is an artist's impression of what Madhava might have looked like. I'm sure there is no authentic. Yeah. But this is the Madhava pi series. And this in the Western literature is called the Madhava-Leibniz series, or the Madhava-Leibniz-Gregory series. Suvrat corrected me in one of my talks that it should just be called the Madhava series, and mathematicians actually call it the Madhava series. So this is an alternating series. The thing to note is that it starts off with 4. And you would have thought that pi is 3.141. Why does it start with 4? It would be nicer to have a series that starts with 3 instead, and small corrections like what we actually do. But anybody knows why this starts with 4? Where would 4 come from? Exactly. That is the origin of this series. But also because of the fact that you would try to approximate the area of a circle by a square by either inscribing or circumscribing. That's the reason why you get 4 out of that. In fact, I'll show you a series where you'll also get 2 as the leading term. So it's not necessarily true that all these kind of series start with 4. There is a very nice combinatorial interpretation of this, which you can find in Hilbert's book. And I strongly encourage you to read that, but I won't talk about that. This particular series is notoriously slow to converge. If you've ever played around with convergence, this is an alternating series. This in the large n limit, it goes like 1 over n. So obviously, if this -1 was not there, it wouldn't converge. And then there is also an ambiguity in how you regroup terms. So in fact, you need to just keep adding terms in the order that they appear. But when you do that, this is notoriously slow to converge. 10 decimal places requires billions of terms. In fact, it requires some 5 billion terms. And I gave this talk because I wanted to somewhere else. And what is the proof that Madhava ever came up with this formula? And this is through the Kerala School of Mathematics. Of course, this audience does not need to be told where Kerala is. And the evidence, at least the historical evidence, is from a treatise by Charles Wish, which was presented in 1832. And he actually gives a lot of details about what the school came up with. And this actually talks about some Hindu quadrature of the circle. And I should tell you that I don't think this Hindu had anything to do with the religion. It's a name that was given by the British to the natives. And you might wonder whether the series was actually written in the form that I showed. It wasn't. It was written in the form of a sloka. And this is a sloka. I won't attempt to read it. But if you translate it, it actually literally reads as multiply the diameter by 4. And from there, you do various manipulations, and that's what you get. And if you recast it in the language of an infinite series, you get the Madhava series. Now, what is impressive so far as I'm concerned is that not only did he find this series, he actually gave a formula for the remainder term as well. So it's if you truncate, then what is going to be the remainder term? So that is something that he was able to write down as well. And in fact, it is there in his work. So this YouTube video is something worth watching. I learned quite a lot about this from this video. Now, the other player in my talk is Leonhard Euler. And Euler invented a lot of mathematics. He actually invented E. This is sometimes referred to as the most beautiful equation in mathematics because it relates imaginary numbers and two transcendental numbers and an integer. He invented the gamma function, the beta function, the Euler-Zeta function, the analytic continuation of which plays a role in the Riemann hypothesis. And also what is less known is that he also popularized the notation pi. So pi in his times was actually twice the value that we use today. What was called pi, of course, pi is pi, but the notation pi was popularized by him. But what is remarkable is that he went blind towards the end of his life. And in fact, in this picture, this portrait, you can actually see, I don't know why he's wearing this weird headgear, but you can see that his right eye is squinted. So he was already going blind at that point of time. And he went blind towards the end of his life, lost his house in a fire, lost his wife, but his productivity still increased. He actually hired a bunch of scribes to write down the mathematics that he thought about in his head. And his productivity increase has nothing to do with his loss of wife, I assure you. But you know, he produced 25,000 pages of mathematics. So you go to the internet, you'll actually see the Euler archives. It's just brilliant and very inspirational. His work continued to be published 50 years after his death. And as I tell various people whenever I give this talk, this is what you should aspire to be. That your wife lives, not your wife, your work. Your work lives on 50 years after your death. Yes. And the Euler-Beta function is going to play an important role in our story because that's where string theory starts. Now, Ramanujan's pi, which is going to be this last half or last quarter of my talk, writes down 17, so Ramanujan's paper, and this 1914 paper actually writes down 17 formulas for 1 over pi, and some of these formulas look like this. Now, this notation here, if you're unfamiliar, is the Pochhammer symbol. I'll define it more closely in a bit. Now, compared to the Madhava series, you will see these integer powers in the denominator. So there is a 4 to the power n, and also these higher powers, n factorial cubed. In the Madhava series, you never saw an n factorial. There was just an n in the denominator. And so you could suspect that this must be converging much faster. In fact, it does. If you look at Ramanujan pi Google search, this is a frequently quoted formula that is there in any of these Ramanujan pi series. It's a remarkable formula. I'll explain to you where this formula comes from. Now, the question, at least as a physics talk, is going to be that in the Madhava series, there is this infinite sum over n. In the Ramanujan series, there are these infinite sum over n, and there are these weird objects. Do these objects have any physics interpretation? So that is going to be the kind of questions that you can have in your mind when listening to this talk. Now, whenever I give this talk to a diverse audience a few days back, and nobody knew who Ramanujan, not nobody, some people did not know who Ramanujan was. So it's quite inspirational to see his entry in Wikipedia. So it says Srinivas Ramanujan Iyengar was an Indian mathematician, often regarded as one of the greatest mathematicians of all time, though he had almost no formal training in pure mathematics. Of course, he came up with these fast converging formulas. The modern world record, Well, the world record of computing trillions of digits of pi actually were motivated by these kind of this kind of work. And this was written in 1914, and the systematic proof was only found by the Borwein brothers in the 1980s. And so they wrote a treatise on this, and the treatise is called Pi and the AGM. AGM stands for arithmetic geometric mean, and that it's a way of actually coming up with an iteration of writing down infinite series. And so that's what I just now said, that is there a physics story? What is n? What do these numbers mean? Are these just isolated mathematical formulas, or is there a more interesting story to say about these? And I should say that this is work in progress with my graduate student Faizan Bhatt, who's going to graduate this year, and he's going to go to Italy for a postdoc. So, of course, a measure of success nowadays doesn't stop with what you write, what your paper is whether your formulas have appeared in movies. So these first two formulas that I write here actually have made an appearance in a movie. It's called High School Musical, starring somebody called Vanessa Hudgens. I don't know who this person is. Anybody in the audience knows anyway. And these two formulas were written in a blackboard, and it says that apparently the teacher had written this formula wrong, writing 8 instead of 16, and Hudgens, who was supposed to play a very prodigious mathematician, caught that mistake. And of course, it's also a good question what Ramanujan would have done had he had access to computer algebra packages. And so I also wondered about this question. And so it's a matter of debate. Maybe he wouldn't have been able to come up with these formulas, but then this is actually addressed, at least the Borwein who wrote this treatise on Ramanujan's formula seemed to say that. And this was written in 1987. So he said that he died in 1920. Had he not died so young, his presence in modern mathematics might be more immediately felt. Had he lived to have access to powerful algebraic manipulation software such as Maxima. And I'm very pleased to say that I'm not old enough to know what Maxima is. But maybe some of the people in the audience, Ashok probably knows what Maxima is. Yeah. Is it around? I've never used it. I see. I've never used it. But anyway, so this is some... I see. You use it? I see. Oh, I see. I see. Interesting. Thank you. And so anyway, so if had he had access to these, who knows what he would have done, but maybe there's a counter to that. Maybe he would have become lazy, and then he wouldn't have invented any of his great work. So anyway, so do these series have a physics story? And the punchline, I'll tell you the punchline first. So there are infinitely new formulas for pi, starting from string theory and quantum field theory. So one of them is this one. So I'll parse this formula. So this is going to be an infinite sum. And the first term in this infinite sum inside this bracket, minus 4 over 2n plus 1, you should recognize. This is precisely the combination that appears in the Madhava series. And then there are other stuff. So this is a Pockhammer symbol. So let me just tell you what a Pockhammer symbol is. It is a generalization of the rising factorial. It's simply a subscript n is a into a plus 1 into a plus 2 all the way up till a plus n minus 1. So if you substitute a as 1, you get the ordinary factorial. In this formula, you see a new parameter lambda, which does not appear on the left-hand side. Now, this formula holds for any value of lambdas as long as the real part of lambda is bigger than minus 1. There is an analogous formula where you have this subscript of the Pockhammer replaced by n rather than n minus 1. And there is a trivial change of sign, which comes from the Euler-Beta function. The formula that I wrote here came from the superstring amplitude. I'll tell you where this comes from. And the restriction on the real part of lambda being bigger than minus 1 actually comes from the convergence of this series. It can also be seen from the dispersion relation that I'm going to use to derive this formula. So you can put in whatever value that you want for lambda. It could be a rational number. It could be an irrational number. You'll always get pi. And so this formula does not exist in the mathematics literature. So after a paper came out, there was some debate. I had posed this question in the Math Stack Exchange, and before our paper came out, nobody bothered answering that question. And then after a paper came out and it got some discussion, they started acknowledging that this paper does not this formula does not exist in the maths literature. So one thing is that if you take lambda to be much bigger than 1, then this formula is exactly the Madhava series. So imagine that you have truncated the sum at some point, and you have taken lambda to infinity, then you can see that the sum becomes exactly the Madhava series. Maybe it is not completely obvious, but if you look at the formula, then you can actually rearrange this term and make it into an n factorial times minus 1 to the power n, which is exactly what appears in the Madhava series. Yeah. It has got nothing to do with the decimal places, decimal digits of pi.
Why am I I mean, like you look at sum of 1 over n squared, it's pi squared by 6 or something. That's of interest because it tells us how to sum 1 over n squared.
Right.
But the fact that you get pi on the right hand side, we can compute pi in many different ways. So why is it still an area of active interest to find new series for pi? I mean,
for mathematicians.
Yeah, probably many series you can find for pi, right? Is there some?
So I think mathematicians, it's more an interest from a computer science point of view, that whether there is an existing limit of our computational power as of now to compute. I mean, what is it that prevents us from computing, say, 10 to the power 40 decimal places?
So the question is to find more faster converging series. To find a series that converges.
Right. I mean, as far as I can make out, it's a computer science problem. Why they want to calculate. Because so far as physics is concerned, we hardly require more than 5 decimal places to calculate anything of great accuracy. Yeah.
Pseudo-random generator sort of yeah. So
because it's a unit.
So you kind of, once you have lots, then you can use it as a resource for.
Oh, I see.
Pseudo-random generation. My big memory.
Is it series faster converging than known series?
This is faster compared to the Madhava series. It is definitely not faster compared to the Ramanujan series. Yeah. So this is only from where did this formula come from? Why you have this interpolating function between Madhava series and some other known formulas? So that is the kind of question why we are interested in this. This is not how we came up with this anyway. So I'm actually presenting the talk in the reverse logical order than what we presented in the paper. Okay, so there's some interesting properties. So in fact, if you dial lambda, then the positivity property of this series also changes. So for example, if lambda is between these numbers minus quarter and 1, then each term is in the summand is negative. And that's exactly what you want because the first term is 4. So it'll be nice to have some fast converging negative number that gives you 3.14. But this is not Madhava series which alternates in sign. So that is an indication that you'll get faster converging representation compared to the Madhava series. And there is also some interesting thing that you could get an approximate polynomial equation if you put lambda equal to some integer multiple of pi. And the truncation gives you a polynomial equation for pi. And if you play around with that polynomial equation, it has only one real root, which actually corresponds to the closest approximation to pi. It's bizarre, but that's the experimentation that we get. And I should tell you that there is a proof by mathematician Hjalmar Rosengren, who found a general proof of this and other formulas in our paper for the Euler-Beta function meant for mathematicians because mathematicians did not understand our paper. So they wanted to devise their own formulas. And the punchline for Ramanujan pi and CFT, and this is something that is work in progress, is that all Ramanujan formulas are of this particular form. So there is some Pockhammer, and then there's some sigma here. And A and B are algebraic numbers. So algebraic numbers simply mean that they're of the form surds and they satisfy algebraic equations. There is some Z here, Z raised to the power n. And so all these formulas are generically of this form. And sigma here belongs to one of these rational quantities, half, 1/3, 1/4, 1/6. Now what yes. Which one? Yeah.
Some very high degree polynomial or?
No, you can start with, say, truncating up till three terms.
Right.
And then, so this would be a degree 2 polynomial because, and so you'll basically get probably a 4th order polynomial equation whose solution is pi, an approximation to pi.
Okay.
Not exactly pi, of course.
4th order, you can probably just write down a solution?
Yeah, so you can fourth order up till fourth order, you can actually write down all possible solutions. And
yes.
yeah.
So that will just be like some bunch of square roots.
Yeah, exactly. Yeah.
And that will be an exact formula.
Yeah, yeah. Exact, not exact. An approximate formula for pi. Because you're truncating here, right?
Oh, if you truncate.
Yeah.
Okay.
Polynomial equation only if you truncate. Otherwise, it won't.
Then otherwise it's not a polynomial.
Yeah.
Okay, sorry, I got confused.
Lambda is a multiple of pi, integer multiple of pi. You wanted to choose to do this.
Yeah.
That's better. And you could have put lambda to be any multiple of, pi by.
It could be anything. Yeah. And integer multiple of pi was just an example. It could be any multiple of pi. Yeah. Rational multiple so that you get nice looking formulas. Yeah, so that's why real part of lambda is bigger than -1. Yeah. Okay, so what I will argue is that these formulas actually are related to a calculation of 4-point functions in a specific 2D CFT. It's a logarithmic conformal field theory with negative central charges, and these sigmas map to these central charges. So sigma equal to half will map to C equal to -2 1/3 to -7 1/4 to -25/2, and the last one to -24. Z here is going to be related to, not exactly, but related to the conformal cross ratio in what is called the diagonal limit in the CFT literature. And these formulas arrive from 4-point correlation functions. For example, in the C equal to -2, you would be calculating the 4-point functions of what are called twist operators. So there'll be particular operators of dimension of a particular dimension, which I'll specify later. And I should also mention here that these different Ramanujan formulas have different convergence rate. And one particular question that you could ask in the language of CFT, you can ask is, what is the minimum number of operators needed to give you 1/pi? And the answer, very surprising, will turn out to be 1. And so that is something that I will tell you later on in the talk, how it comes out.
One of the formulas you showed earlier had a -1 to the n.
Yeah.
But none of these have -1.
Yeah, so as I said, so Z here depends on, yeah, but that is very observant. In fact, so if you try to prove any of these formulas using the Sommerfeld-Watson transform, then the guys that have -1 to the power n will be particularly hard to prove, because -1 to the power n gets mapped to e to the power I pi z. Yeah. It's a Sommerfeld-Watson transform is, if you do infinite series, you might, instead of doing the infinite series, you treat n as a complex variable, z, multiply the summand by pi cot pi z, and then integrate. And then, so pi cot pi z is going to have poles all along the real axis, integer values on the real axis. Because of this n factorial, the negative guys don't contribute. And so you pick out, and you deform the contour, and pick out the contributions from elsewhere. Okay, so the new formulas, and these are not very useful formulas, I should tell you. But then it's the kind of formulas that come from log CFTs. It's curious to note that you'll get logs. But then, for example, 4/pi this guy actually gives you pi up till some 10 decimal places or something like that. So it's some bizarre looking formulas. I'll show you a more interesting looking formula that comes from CFT considerations later on. Okay, so that's not the point of this talk. It's just to say that CFT considerations, and you learn something from both sides. You learn something about mathematics. You learn something about the physics involved. Okay, so the underlying motivating question is, what is the best basis to expand an amplitude or correlator? And the question is it the Feynman diagrams or Wheaton diagrams, or is it some string worldsheet picture? Is it some partial wave expansion or something else? And at least so far as the purpose of this talk is concerned, my story is going to be heavily based on something which I call the stringy dispersion relation. This is a non-standard terminology, but since we invented the maths, we call it whatever we want. So this is what I will call the stringy dispersion relation. So what is the motivational question? So you open Wheaton's no mass review, and you can open any textbook, but this is something that you learn, that contrary to quantum field theory, so suppose you had colored scalars and you're scattering colored scalars, so you'll have two channels in this particular description. So if you had identical scalars scattering, then you would also have the third channel, but in this particular case, you have only two channels. So you would, in the quantum field theory language, you would sum the S channel and the T channel diagram. Whereas in the string picture, you fatten up the external legs and you get a world sheet. And if you look at this world sheet, then there is some way of stretching this world sheet into this picture. So this fattens up into that diagram and this fattens up into that diagram. But from the string theory perspective, both of these are same because you can stretch one into another. Because there is an underlying symmetry, a conformal symmetry that enables you to do that stretching. Now, on the other hand, in the quantum field theory language, when we actually describe in generality these scattering amplitudes, we use what is called a dispersion relation. So this is nothing but a fancy application of Cauchy's residue theorem. You know where the poles are. If it is tree-level scattering, the poles are going to be corresponding to these discontinuities. The discontinuity of a pole is simply a delta function. And you write down a dispersion relation. So you write down Cauchy's residue theorem. You pick up the discontinuity. You hope or you know from somewhere that the arc at infinity goes away, and you get basically the contour becoming just a real line integral starting from the location of the first discontinuity up till infinity. Okay, so that is the dispersion relation. So this is a 2-to-2 scattering. So 2-to-2 scattering is a function of two Mandelstam variables. So when you write down a dispersion relation, you hold the second Mandelstam variable fixed. So this is what is called a fixed T dispersion relation. So we are familiar with the fixed T or fixed S dispersion relations. But from this non-perturbative description, this is a non-perturbative description of scattering amplitude. The question to ask is there a way to deform the fixed T into a fixed S dispersion relation like this picture seems to suggest? And if so, what is the deformation parameter? And this is the question. So in other words, can we come up with a string flavored dispersion relation which actually captures this picture? Okay. Is the motivation clear? The answer is yes. And this is based on work, so largely based on the first two papers. So the first one was based with Arnab. It appeared in earlier last year. The second one was co-written with my graduate student Faizan Devopriyo, who's also my graduate student in Arnab. And the third, which is going to talk about this Ramanujan series, is work in progress. And this uses heavily earlier work that we did with Ahmadullah and Prashant. Ahmadullah was my graduate student. Prashant was a postdoc. And I should actually point out that this line of research originated by considering critical phenomena. So what we were exploring there is basically a new way to do the bootstrap, the conformal bootstrap in Mellin space. And this was done with Rajesh and other graduate students over the last several years. So the picture that you should have is a new kind of dispersion relation, which actually interpolates to all the known dispersion relations. So this coincidentally worked out to be the familiar diagram that you have in M theory, so it must be correct, because once you have a picture of this kind, it must be right. So what is going to happen is that there is going to be a parameter in my dispersion relation. It's similar to the parameter in the pi formula lambda. And taking various limits, you actually approach all the known dispersion relations. So fixed T, fixed S, and fixed U should be familiar to you. So there are three Mandelstam variables in 2-to-2 scattering. And fixed T means you're keeping T fixed and so on. CSDR stands for crossing symmetric dispersion relation, and LCSDR corresponds to local crossing symmetric dispersion relation. This crossing symmetric dispersion relation was invented, or the first written down by Oberson and Khoury in the 1970s, and this is what we actually resurrected in some work, in particular in the work with Ahmadullah and Rajesh and Ahmadullah in 2021. And the local crossing symmetric dispersion relation is motivated by a work that was done by a statistical physicist by the name of Chao-Ming Song, which is going to be the main thing. Yes. I have not shown the dispersion relation, but yeah, this one, yeah. That's right. Yeah. Yeah. So that is. So it dies off faster than S. Yeah. If it is crossing symmetric, then yes. Okay. So yeah.
So this is specifically for string amplitude.
So this particular thing that I'm going to tell you about and the dispersion relation that I'm going to tell you about is going to be for the string amplitude.
So
but you.
Infinity.
Yeah.
Is specifically for string.
Yeah. Yeah. But there are higher subtractions, very easy to write down, which are generalizations of these dispersion relations. They will have subtractions, but those are basically in the same spirit. They look similar to this. Yeah. So they will start depending on the subtraction point, which is up to you to choose. But it's basically the same. It's just Cauchy's theorem. So long as it does not die off super exponentially or something like that. If it is power law, you can always write down something like this. No, I mean, so it could be anywhere. It does not have to. So in this particular case, to convert the contour integral into a real line integral, I am assuming that there is only a cut. But in principle, you can do the deformation as long as you know that where the discontinuities are. You can always do this step. Yeah.
You are doing 3 amplitudes, right?
Here in my story, I will focus on 3 amplitudes. The formulas that I'm going to show apply more generally. So that we have checked with box diagrams and loops and things like that.
But for you, the amplitude has only poles.
Yes, for me, the amplitude has poles on the real axis. That's right. Yeah. In the CFT case, there'll be cuts because in the CFT case, the discontinuity will be of hypergeometric functions. I mean, in both these stories, this will play a role. Okay. So, so this is the outline for the rest of my talk. So I'm going to first discuss about the bootstrap origins of string theory because I'm very fond of the history behind the string theory, and it's worth learning a bit about that. Then I'm going to tell you about the stringy dispersion relation and how this pi formula came about. And as an application, I'll briefly mention the stringy bootstrap. Maybe I'll skip it depending on how much time I have. And then towards the end, I'm going to talk about this new work. Okay. So let's talk about the bootstrap origins of string theory. So I showed you this picture before. Now, I don't know how many in the audience have actually read Green-Schwarz-Wheaton. So I know the senior people must have. So by a show of hands, how many of you have read Green-Schwarz-Wheaton? Okay, Ashok, I was worried Ashok is not raising his hand. I was going to ask you, where did you invented string? Okay, so if you read the introductory chapter of Green-Schwarz-Wheaton, you will see this, this caveat, and this is an important caveat. The duality hypothesis is just the equivalence of these two diagrams. Never had more than slender experimental support, and the Veneziano model was merely an ad hoc way of satisfying this not so well-motivated hypothesis. Okay, so we should take this caveat very seriously and ask, so why is this caveat in place in the first place? Because this is what string theory started with. And there are several more confusing statements in the literature, which I think were never clarified in writing. So depending on who you talk to, I think the clearest statements, to be honest with you, the clearest statements that I ever found about this was discussions with Ashok, which I'll clarify in a bit. And the kind of confusing statements were, so if you open Stanley Mandelstam's beautiful physics reports on the dual resonance models, he'll tell you that, okay, you know, if you consider composite narrow resonances, then you're not supposed to sum over channels, but rather the sum over these poles is supposed to be equivalent to the sum over the other poles. Whereas if you really talked about quantum field theory, you'd require to sum over channels. A more recent review is this beautiful book, The Birth of String Theory. Now, I call these beautiful because when you actually read these, the description of the work, you'll actually feel some of the pains that the workers felt while working or trying to develop string theory. So for example, you will encounter this phrase called double counting. If you open John Schwartz's work, he'll talk about double counting. Noether's work also talks about double counting. Michael Green's work also talks about double counting. So it's as if saying that if you really thought about adding the S channel and T channel, you'd be double counting, because if the duality statement was true, the sum over S channel was already giving you sum over T channel, so you don't require to add these two. But there is this calculation, and this is something that I learned. So if you want details, then there are two sources. One of them is chapter 9 of Polchinski's volume 1, and the other source is Ashok's paper from 2019. So this is what is called the plumbing fixture construction. You can do it for open string, but I was lazy. I did not rewrite my slide for the open string. I just did it for the closed string. So suppose you were calculating the sphere diagram. You'd have 4 vertex operators on the sphere. But there is another way of doing the calculation, which is basically you glue two spheres together, and there are two other ways of gluing. And what you do is you choose local coordinates at the point of these punctures. And in the choice of local coordinates, there's a free parameter that is left over. And this free parameter for convergence reasons, or no, not for convergence reasons, for the reasons that it has to cover the entire moduli space, has to be bigger than 3. So it cannot be some arbitrary number either. And what happens is that in order to cover this entire moduli space, you just cannot add these 3 channels. You also require to add contact diagrams. These contact diagrams from this picture actually comes from integrating the integral that you started off with in this white region, which is devoid of any singularities. So if you want to know more about this calculation, I refer to you these 2 sources. So the lesson to learn is that you can have a decomposition of the usual string amplitudes in terms of channels, provided you add contact terms, and provided you also have, or at least one lesson is, that this decomposition actually depends on this parameter lambda. So depending on what choice you make, you get different decompositions. So the convergence rate is controlled by lambda. The larger lambda you choose, the series converges faster. So the contact terms in this picture is actually an integral over this area. Yeah. What happens? I forgot. Yeah.
The larger lambda sector, most of the contributions from the Feynman diagrams are very small region, cover small region. So contact diagram will start.
Okay, so there is parameter lambda, and now so I want to talk about standard representations that are known in the mathematics literature, and whether they actually have this feature that you should be able to see the poles in the variables in the S and T variables, and you should also see some parameter like lambda appearing. So are there some known formulas? So series representations that are known. So this is the Euler-Beta function, because that is the open string amplitude. The one corresponding to the previous slide is the Virasoro-Shapiro amplitude. There is a similar story. I will flash formulas for that similar story later on. But let's go back to the open string. So this is the Veneziano amplitude. So this will be like the Euler-Beta function. You open this big fat textbook called Grashstein and Rijik, and you see what formulas you can find from there. So you will see that there is a formula which actually sum over poles in either the S1 variable or the S2 variables, but not both. And as a result, you get a limited domain. So the real part of S2 here in this sum has to be less than 0 for convergence. Otherwise, you won't see the poles in S2. And that's obvious that this guy has poles in both S1 and S2 whenever S1 and S2 are integers. But this only makes manifest the poles in one channel. So obviously, it has to have a restricted domain of convergence. And similarly for the other case. And this is the statement of duality. The fact that the S channel poles is equal to the sum of the T channel poles, provided that you are aware of this restriction. Something that is not quoted in the string literature, which I find very surprising, is the other representation, which is in the modern language, it can be called the fixed Q representation. So there's a coordinate transformation, and you can find that coordinate transformation in our paper, or you can open Grashstein and Rijik and look at the integral, which actually makes this infinite series manifest as well, where actually you have sum over poles in both channels. It's dressed by some Pochhammer, and again you have a restricted domain of convergence. The real part of S1 plus S2 has to be bigger than -1. And for some mysterious reason, this formula, which on first sight seems to contradict this duality statement, is rarely mentioned in the string literature. The only place that I found was some 1970 or 1971 paper by Nakanishi. And either ways, neither of these formulas meets the string field theory expectations that the only non-analyticity should be at the poles and not somewhere else in the complex S1, S2 plane. And neither of these formulas actually exhibits this parametric ambiguity, this dependence on this lambda that string field theory is supposed to teach us. Yeah, because this series only converges when real part of S2 is less than 0. So if you, for example, this does not converge if you chose S2 to be 5. Yeah, you don't see the pole. Yeah.
So this one,
Yeah.
these are the correct residues, or these also?
Yeah, no, this has the correct residue. Everything that I show, all the formulas that I show, all have the correct residues.
No, the correct residue, I mean, that if you just naively pick up the A1 over N minus 1, right?
Yes.
And that residue.
Yes.
That is a full residue at S1.
Yes.
Okay.
Yes.
So there's nothing coming from the other side.
No. No. Yeah. Now let's go because this is historical. Let's go back and see what Dolan, Horner, and Schmidt actually said in their paper, because this is Dolan, Horner, and Schmidt are credited to have started this duality hypothesis business. So now I should point out that if you open Dolan, Horner, and Schmidt, which is this paper written in 1967, wherein Ziano's paper was in 1968, this S equal to T statement, they're very conservative. This is not what not all what DHS said. So they were actually looking at experimental data. They were looking at scattering data. This would be a pion-proton scattering data. They actually make this claim that the data seems to suggest that the correct prescription for the amplitude description should be something that they call the Regge amplitude. So this you can think of as the T-channel poles, something that they call the resonance amplitude, which you can think of as the S-channel poles, and minus some average. And this average I will make precise. This average is going to be identified with these contact diagrams. And they want this average because otherwise, if this average wasn't present, data seem to suggest that this would overcount the amplitude. And then they actually make some statement that if the resonances overlap, then this guy and this guy would be the same, and as a result of which you'll just be left with the amplitude being the sum over the T-channel poles. Okay? So this is some, if you think about it, and if you read their statements, this is some suggestion that they have. And the thing that they definitely ruled out is what was called the interference models in those days. Interference models simply suggested that you should just sum over the Regge and the Regge rather. My Italian friend tells me that it should be Regge, not Regge, and the resonance. Okay, sum over S channel and sum over T channel is something that does not fit data. Okay, so this is something that you should rule out. So it really seems to question whether there's a different way of actually explaining the original data, the experimental data, which string theory anyway has so far failed to explain. So this is a good place to bring about a quotation by Polyakov. The garbage of the past often becomes the treasure of the present and vice versa. Now, what is the garbage of the past and what is the treasure of the present is open to interpretation. So I will leave that to you to figure out. But the resolution to this and this series, which one?
Treasure of the past becomes
That is also that could also happen, you know. So it's yeah. Anyway, so what we are shooting for is a new kind of representation for the Euler-Beta function. It should actually have manifest poles in both channels. It should have this parametric ambiguity, and each channel should converge. Because one thing that I forgot to tell you is that the sum over each channel in the string field theory calculation converged on its own. The contact, whatever was identified as a contact term, also converged on its own. Okay, so you want a series representation of that kind. And no, so this new series representation does not require that constraint. So this converges everywhere in the complex plane. Okay, this has precisely the features that the string field theory calculation taught us. Yeah, that's right. Yeah. Yeah, I mean, it's easy. I mean, you take this formula, go to Mathematica, ask it to calculate the residue, it will do it. Okay. So the formula here is what I've shown for the Euler-Beta function itself. The formula, sometimes I will put a 1 in the denominator because that is the form factor that arises in the superstring case. And sometimes this 1 is going to be missing. So whenever you see a 1 here, then you have to replace this Pockhammer by n minus 1, but it's a trivial replacement. No, it doesn't. So actually it cancels out. So if you actually put S1 equal to n, you will see. So we can do this calculation. Yeah. It is related, but I can't. So there it was some leftover residual freedom that you had after choosing coordinates. So here I will. I mean, I can't argue that this is related to some worldsheet calculation. So
It's in the same spirit, but
yeah, it is in the same spirit, but I can't really make that identification. Yeah, that is very true. The largest behavior. Doing this sum directly and verifying the largest behavior is it's actually non-trivial. So what you have to do is, again, if you wanted to study the largest behavior, there are two ways. Either you do it numerically, which we have done. You can actually take various limits, Regel limit, Hart scattering limit, and you verify that it has exactly the same, it reproduces the left-hand side. Or you can do the Sommerfeld-Watson transform, and then actually go back and reproduce this series. So this new series actually manifests poles in both channels. Each summoned here, this piece, this piece, this piece, is analytic on its own away from poles and has this parametric form, which you can interpret in the language of field definition ambiguity, because that is what you want to interpret this lambda from the point of view of string field theory. Now, this does not exist in the literature, and the reason is because of the argument here. Now, if you remember the formula that I presented before, this one was linear in n. This argument here was linear in n, or the n was absent. So here what has happened is that you have an n in the denominator, and that is actually very tied in with the fact why this series converges so well. Individual terms, why they converge so well. And this kind of a series cannot be identified with a hypergeometric series. Rather, they are generalizations of hypergeometric series. And the reason why this was absent in the literature is that because it uses a new kind of a dispersion relation, which did not exist before our work. And as I mentioned,
it's one minus n, no others.
Yeah.
Then also it converges the sum over n.
Yeah, that's what I said. So each individual piece converges. Yeah. Exactly like string field theory taught us. Yeah. And and this is where the pi formula comes in. You just put S1 equal to minus half, S2 equal to minus half, and you get a formula for pi. And I told you that there are interesting series where the leading term in the pi series is not 4 but 2. And if you look at this series, it takes a bit of work to actually convince yourself that the leading term here actually changes from 2 to 4 as you dial lambda from 0 to infinity. And you get interesting new series representations for all these data functions as well. Now, there are other bootstrappy reasons why you might want to desire a truncated representation. So this kind of a thing, you can truncate and you capture all the interesting features that the string theory amplitude has. And why do you want to do that? It's because we know that string perturbation theory is going to break down if the center of mass energy is bigger than this quantity here. So if you are at a fixed coupling, then there exists some center of mass energy beyond which there will be black holes as intermediate states. And if you wanted to study this problem using the bootstrap, we should match perturbation theory up to some energy scale to a non-perturbative representation and search for signatures of black holes as intermediate states. So you really have to consider a truncation. So you require an amplitude which where you can truncate the tree level answer. So I said that this lambda is related to field definitions in what sense? So let me just very quickly tell you that. So imagine that you had a simple theory where you had light particles and heavy particles. And suppose the light particles were interacting with this heavy particle, the heaviest particle psi2 here, through this cubic interaction phi1, phi2, psi2. Now you just redefine psi2 in this way. And then a series truncation in the language of this infinite series that I've been talking about is simply deleting these heavy fields. This is not the procedure of renormalization that we are familiar with. This is just deleting heavy fields from your Lagrangian. Now, because you have done this field definition, if you do this field definition and then drop the psi2 terms, you'll be still left with these light field terms, lambda, phi1, phi2, phi1, phi2. And this is going to be a contact interaction. This interaction term is going to give you an additional piece, which is going to be the contact interaction. And so this new term only depends on these light fields, and this is the imprint of these heavy fields. So if we truncate in these heavy fields, then the observables involving only light fields will know about these heavy fields through this ambiguity. And this is this parametric ambiguity in the series. And this is how you interpret the contact terms. The ambiguity is only in the contact terms. The residues don't depend on lambda. So that is one lesson that you learned anyway. The ambiguity is only in these polynomial extra pieces. And this is the reason, or this is a simple way of thinking about that ambiguity. Or you can think of it as some kind of a stretching parameter, where actually you have a non-perturbative representation of this kind and you stretch it into string diagrams. But I don't want to actually make too strong a claim because I don't really know when one can call something as a string diagram. So this is the dispersion relation. So finally, we come to the main formula, and the derivation of this formula is non-trivial, but I can give you some hints as to why this formula is correct. So this is what I call this web of worldsheet dualities, the dispersion relation that actually interpolates between various known dispersion relations. So there is a kernel, and the kernel is reminiscent of what you would get in a phi cube theory. So it's like a phi cubed interaction because the sigma is getting integrated over. So you can think of the sigma as a mass parameter. And the first two terms are exactly what you would get in a phi cube theory. This guy is something that you would get in a phi 4 theory. This is like a contact interaction. There is no Mandelstam variable here. And this is the discontinuity or the absorptive part of the amplitude. And except that we are doing something non-trivial, the first variable is always the integration variable, but the second variable is what we hold fixed. So this you would have thought in the fixed T dispersion relation, this would be S2. This we replace by a non-trivial quantity like this. So this becomes, instead of S2, you get S1, S2 shifted divided by sigma, and that is why you saw those 1 over n in the formulas, because the sigma appears in the denominator, minus lambda. Now, this is not something that we cooked up. This actually follows from a derivation, and the derivation is hard to explain in a short amount of time, but we can actually go through why it reproduces the known results. So, for example, if you took this limit where say lambda was becoming minus S2, then you can see that this term and this term would cancel out, and you would get only this term surviving. So lambda is becoming minus S2, lambda is becoming minus S2, this goes away, and this minus lambda becomes S2, and this is precisely the fixed T dispersion relation. Okay? You can do a similar replacement where sigma lambda is minus S1, you get the fixed test dispersion relation, you take lambda to infinity, you'd get the two-channel symmetric dispersion relation, which is the fixed U dispersion relation, and so on. And this I have no time to explain, but there are limits where actually you can interpolate to the crossing symmetric version and also the local crossing symmetric version. So all these known dispersion relations, which were originated with this work by Auberson and Curry in 1973, and what we looked at earlier in 2021, is captured by this single formula. Okay? So this parameter here is that parameter that we learned from string field theory, that there should be some parametric ambiguity. And so it's tempting to think that there should be some way of connecting up with the worldsheet, but as I said, I really don't know what extra things I should add to this setup before we start calling something as having an underlying worldsheet description. The constraints, on the other hand, this amplitude satisfies some constraints. One constraint is that it is independent of lambda.
Theoretical interest, other is pure practical interest. Right. Your theoretical interest is that does mean field theory become exact in the limit of Q going to infinity?
I knew somebody will ask this question. We have not examined Q going to infinity.
I think some other talk is going on in parallel. Yeah, so that's a good exercise to do. By the way, the fact that the left-hand side is independent of lambda gives you constraints. So any derivative of this amplitude with respect to lambda should be equal to 0. And that will be a constraint on the partial wave expansion of this absorptive part. So as I said, that this is how you get, and then precisely this is what happens, that if you set lambda equal to minus S1 or minus S2, you recover the known representations, which are these representation 1, which manifests duality. If lambda is much, much bigger than 1, then this interpolates to representation 2, which is again a known representation. So this actually interpolates between various known representations. And this kind of representation actually makes it very tempting to suggest that there must be a truncated Lagrangian where you have these cubic interactions with higher spin vertices if you add suitable contact terms to describe the physics within a certain disk. And this is the new formula. So this is where this was the thing that I started off. And if you look at this new formula, it converges at different rates. So for example, on the x-axis, I have the number of terms. And on the y-axis, I am dialing lambda. So lambda equal to -12 is what you could claim to be the string worldsheet representation. And lambda infinity is a Madhava series. So the fastest converging representation is somewhere in the middle, which you can think of as in the language of Feynman diagrams. So this is some kind of an extra controlling parameter that you have, an extra coordinate, which gives you different rates of convergence as you dial this coordinate.
Equal to this one is to both equal to
-12. Yeah. Yeah. You have other fractional values which will again give you different kinds of pi formulas, but I just focused on that. Yeah. So because you can truncate, I was simply making the point that you can truncate this series, and this series captures all the stringy features within a disk. Within a disk where mod of S1 and mod of S2 are less than the truncated value. And so that would suggest, and because of the fact that you have only polynomials coming from these contact terms, that you should be able to write down an effective Lagrangian of this kind, where you're truncating in the spin sum and also the mass level sum, which captures the same physics. So this is something that somehow captured the attention of the general public. It was covered by Scientific American. But nowadays, there are metrics for everything. Nowadays, there's a metric for popularity. So popularity, how popular is your paper? So there's something called an altmetric score. Okay. So somehow APS actually makes this, gives you the altmetric score, and most of the altmetric scores are embarrassing. You click on your altmetric for all the other papers, it's like 1 or something. This has an altmetric score of 570. And this actually is because it got a lot of popular coverage. And this also is, of papers of similar age is the #1 paper in PRL. Okay, and it is in the top 50 paper of all papers from PRL. Okay, and I should tell you that one of the best compliment came from some YouTube channel, which made a which made a popular level coverage of our work. And some YouTube viewer had commented, string theory is not as useless as I thought. So this is vindication that we are on the right track. Okay, so yeah.
So yeah, lambda ambiguity is so one way, I guess, which even what you said in terms of this Lagrangian and earlier, that it's related to a field redefinition ambiguity. But you also want to say it's related to some worldsheet ambiguity in the system.
Yeah.
So it could be, so it kind of
suggestive that
the worldsheet redefinitions lead to some space-time.
Yeah, that's what happens basically. That in the worldsheet picture, those coordinate choice that are in the right? If you just change lambda, that you can show is equivalent. That changes the string field to the axis.
Right.
But that's equivalent to redefinition of the string. So deformation of lambda you can remove by redefining.
But then, right. Okay.
And default lambda basically determines how much is covered by the Feynman diagrams and how much by the contact. This lambda, I don't know, this lambda is somewhat different, but it's in the same spirit, but it's not quite that lambda.
Yeah, I can't, because that was a local coordinate choice. I don't know.
You can definitely write, because once I have an amplitude, I can probably write an effective Lagrangian, because
that's right. Because all the Wilson coefficients will depend on this lambda. We should probably call it lambda tilde, because string theory literature, I guess I don't know. I think even Polchinski calls it lambda or something. Yeah. But anyway, so Lambda tilde is some function of lambda. Yeah.
This you see by looking at
Yeah, so the kind of things that you can do is that if you actually change lambda, then the contact terms in my effective Lagrangian will change. That you can check explicitly. We have expressions for the contact term. Another way of saying the same thing is that if you actually calculated the Wilson coefficients, the low energy Wilson coefficients, then they depend on the truncation as well as lambda. Yeah. Similar in spirit to RG. So this I will skip. This is an interesting story because we were actually doing string bootstrap. And one of the underlying things is that, right now there is a lot of effort to try and somehow claim, which appears to me to be a political propaganda, that string theory is somehow unique. And I think we should go in the opposite direction. We should actually try to enlarge the string framework. So you should actually relax the condition that gives rise to string theory and see whether you still can retain some of the good features of string theory. Okay, so this work is actually in that direction where we are trying to ask what are the constraints that gives rise to string theory and how do you relax those criteria and get more interesting amplitudes. So this I will skip, and at the end, if there is any interest, I can explain what this is. That is very true. So this is something that yeah. So it is very possible that all these known things are going to get ruled out. And then ultimately, but if that is true, it's great. And then, of course, you'll have a uniqueness condition. And then you have to really study what are the implicit conditions we put in to get string theory as a unique answer. Yeah. So string theory will be one answer. I'm saying that you will get other answers.
It's not clear you get other answers in this way by deforming string. That doesn't sound like we can't even do it in quantum theory. You can't take a theory and take some amplitude.
No, what do you mean? I mean, you can always add. But these are very special deformations because you are restricting the class of high energy deformation, the high energy behavior. So you can't really add random contact terms and so on. Yeah. So within that category, I mean, we have done a very restricted calculation here. We have just focused on 3 amplitudes. Like Ashok said, that you have to demonstrate that it is non-perturbatively consistent. So when you go to loops, yeah. Not just at loop level. I mean, I guess if loop levels are sort of the same thing as demonstrating higher point function consistency. So I guess in that sense.
Deformations which correspond to some solutions of string theory where asymptotically it's still flat space, but in the middle it is something, some lump or something like that. So those will be also consistent. Right? So you should expect a large family of such consistent.
That is,
This is true. My only concern is whether one can get there
by solving the bootstrap equations. No. So this is not a deformation in the lambda sense, by the way. Lambda is not a deformation parameter. Yeah, it's independent of lambda. So these are all in the space of Wilson coefficients. So as I said, I wanted to skip this because I wanted to actually tell you the Ramanujan pi story. But if you're interested, maybe at the end, if we can have a private chat. Yeah. Oh, I still have half an hour. Okay. Oh, okay. I see. Yeah, so half an hour will be sufficient. I didn't want to rush through the Ramanujan pi story because I think it's quite an interesting story. I wanted to go through the slowly, but if you are interested, then I can tell you this story.
Let's see at the end.
Yeah, okay, very good. So this is the closed string formula, by the way. So this is the Virasoro-Shapiro amplitude, and there is a lambda deformation of that as well. It looks slightly nastier, but this is actually very non-trivial. You see these square roots, and there are these Pochhammer symbols squared. So there is this n factorial square as well. That is not surprising, but this Pochhammer square actually remove these square roots. So there's a way to show that there are no square roots. There are no square root branch cuts that this formula has, for example. These are actually genuinely polynomials in the Mandelstam variables. So you have a similar dispersion relation for the closed string or the fully crossing symmetric case, which one can also study. So anyway, so Ramanujan's pi and physics. I wanted to actually tell you more about this. So Ramanujan wrote a paper in 1914, and I don't even know what this journal is. This is the Quarterly Journal of Mathematics. It was called Modular Equations and Approximations to Pi. This was, I think, the year that he went to Cambridge. So he was there in Cambridge for 5 years, 1914 to 1919. So this is actually based on work done in India. And this paper basically is a collection of formulas, beautiful formulas. Depending, I mean, beauty is in the eyes of the beholder. To me, these formulas appear beautiful. You might find it ugly, but anyway, the point is that he actually came up with these approximations to pi and these infinite series to pi by looking at what are called modular equations. I'll explain what these modular equations mean. And these gave rise to very fast converging representations for 1 over pi. I mean, his main things were, he was interested in 1 over pi later on. And I should also tell you that his papers seem to be very terse on details. And from what I understand, they were terse on details because he could not afford paper. He was doing most of his calculations on a slate and then erasing the intermediate steps. And so he was only writing down the final results. Okay, so the CFT conformal field theory link, I don't have to tell you what a CFT is, but the conformal field theory link here is via percolation. So the kind of questions that people in percolation theory try to address is that imagine that there were 2 kinds of lattice sites, yellow and blue, and there was some probability where one lattice site could be yellow or one lattice site could be blue. Then suppose it was possible, there was a high probability that the lattice site becomes blue, then it's not difficult to imagine that you will always find a continuous path to go from the left to the right. So you could think of that some percolation happening of some drop of fluid, finding a path to go from the left to the right, some channel, some crack opening up, something like that. And there is a horizontal crossing probability and a vertical crossing probability. So this lattice need not be a square lattice, it could be a rectangular lattice. And the aspect ratio of that rectangular lattice is basically the conformal cross ratio that is going to enter the formulas. So these kind of problems pertaining to percolation actually feature in a study of what are called non-unitary critical theories called log CFTs. And these describe physics of percolation, for example. They appear in other studies as well. They appear in the context of turbulence. Not so much as in the context of turbulence. I think Polyakov had an interesting conjecture that somehow turbulence could be described by log CFTs. But they do appear in the study of fractional quantum Hall effect, because the nu equal to 5 halves wave function actually comes from a study of correlation functions in the C equal to -2 theory. C corresponds to the central charge. So the reason why you find this conformal field theory link, and I will just summarize this, is that the starting point of all these Ramanujan series involves squares of Gauss hypergeometric functions. So they're all 2f1 squared. Okay. The original Ramanujan's paper actually focused primarily on a particular class of hypergeometric functions, which are recognized to be complete elliptic integrals of the first kind. So you study simple pendulum and you study the time period. That is what actually gives rise to the full time period without doing the small angle approximation. Okay. So those are the complete elliptic integrals of the first kind that he was dealing with. And because you see a square of Gauss hypergeometric functions, and if you have ever read the Big Fat Yellow Book, or if you have done a course in 2D CFT, you first immediately see this must be in a CFT. So is there a CFT way of thinking about these 2f1 squares? So you would actually open up the Big Fat Yellow Book, go to the section on minimal models, and try to work out the differential equation that gives rise to these kind of objects as an answer to a correlation function calculation. So that's what you do, and that's what I did, or that's what we did. And it turns out that these correlation functions are specific 4-point functions in these log CFTs. I will define the log CFTs more carefully. One game that you can play in the context of this pi story, because I've been talking about pi quite a lot in the beginning, is that you get these new kind of formulas which has these logs. And these kind of formulas arise when you actually expand the correlators in terms of the conformal blocks. So Ramanujan did not expand the correlators in terms of the conformal blocks. Ramanujan expanded the correlators in terms of what is called the Clausen identity. Clausen identity is a special identity that relates specific 2f1 squares to a single 3f2. Okay? So 2f1 squares is like a double sum. Each 2f1 has a single sum. 2f1 squares is a double sum. We are not interested in double sums. We want to write it as efficiently as possible. So it is desirable in this attempt to convert a 2f1 square to a single sum. But in CFT, we don't have that luxury. In CFT, we have two quantum numbers, the conformal dimension, scaling dimension, and L. So we will definitely have to sum over delta and L. Okay, so what is a CFT? So this is a summary, and you can actually, I'm presenting a sort of a lightning version of this calculation. So let's assume a 4-point function. So we have fixed the first of scaling dimensions h1, h2, h3, and h4. And you can actually demonstrate that this has to be the case. You don't have to assume this from the very beginning. But if you open the big fat yellow book, what they do is that the h2, they actually fix to what is called 2, 1. So these h's actually have two entries. If you remember your conformal field theory, they are labeled by R and S, two rational quantities, and you have to specify what R and S are. These are integers. So R is 2 and S is 1. So the first operator is fixed at 0. The second operator takes on values is at z. The third at 1 and fourth at infinity. And you work out the differential equation that it satisfies. And it'll turn out that the differential equation is product of 2f1s. And the product of 2f1s is different from what you would see in a unitary CFT. In a unitary CFT, you would see z here and z bar here. In a log CFT, you see a z here and a 1 minus z bar here. Okay, so it does not have this this sort of whatever the holomorphicity condition that you're usually familiar with.
Dimensions, two independent dimensions on the left. But
yeah.
But on the right, you have only sigma.
Yeah, so it turns out that I will specify what these h's are. They are fixed in terms of sigma. And on the next slide, in the next slide, you will see the formula. Yeah. So you can, so if you look at this Gauss hypergeometric function, then the first guy actually has a log singularity when you expand around z equal to 1. The second guy has a log singularity when you expand around z equal to 0 or z bar equal to 1. So if you are focusing or interested in log z terms, it will come from this, what I call the right part of the correlator. And if you are interested in log z bar term, it will come from the left part of the correlator. So that is worth remembering because that will play a role in my story. So the thing that I'm going to talk about is what is called the C equal to -2 theory. That's a theory of symplectic fermions. Okay, so the first person to, or at least to the best of my knowledge, the first person to have studied this is Hubert Salure in 1991. Yeah. So where does 1 over pi come from? So 1 over pi comes from, in the mathematics literature, it comes from what is called the Legendre relation. So Legendre relation is a specific combination of these complete elliptic integrals of the first and second kind, products of elliptic integrals. But in the language of CFT, they are easier to state. You take this combination of the Virasoro generators. So this is rotation and this is special conformal transformation. Sorry, L0 plus L0 bar is rotation and L1 plus L1 bar is a special conformal transformation. And you apply it on this left part of the correlator and you get sine pi sigma by pi. So that is where 1 over pi comes in. Sigma equal to half is the complete elliptic integral of the first kind. So you actually get 1 over pi on the right-hand side. And you are left with some Virasoro generators acting on the product of two F1s on the left-hand side. And this is the origin of the Ramanujan 1 over pi series. To get the precise forms that he finds, what one proceeds is by taking something like a diagonal limit and using this Clausen identity. I told you that there is a version of Clausen identity which actually converts a product of two 2f1s into a single 3f2 and to get a single sum instead of a double sum. And this last step is a bit subtle. And this is where, so Ramanujan talks about modular equations. So where is this modular equations? What are these modular equations? And this application of the last step is subtle. And this is where these modular equations are applied. These modular equations are of various orders. So let me actually define for you what a modular equation is. Modular equation is a specific relation between two f1s at different arguments. So let's consider the simplest modular equation, sigma equal to half. So when sigma is equal to half and z is equal to z naught, suppose there exists an integer n such that there's a relation of this kind between the two hypergeometric functions. Then this kind of a solution to this kind of an equation would be called a modular equation, and z naught would be called a singular moduli. There is a more primitive version of the modular equation which I will mention later on, but then this is essentially what you have to keep in mind. Now, why is this important? It is because, first of all, you see these 2f1s are transcendental objects, and the fact that you get this kind of a relation between two transcendental objects related by the square root of an integer is indeed remarkable. Because what happens is that these singular moduli are also algebraic quantities. They satisfy algebraic equations. Z naught is not some transcendental object that you cannot solve. So this is what modular theory gives you. This is what modular theory buys you. That Z naught is an algebraic object. It satisfies algebraic equations. It's not a transcendental object. And there are solutions of this kind. This kind of a relation is what is used here because this is the differential derivative operator, and then you have a 2f1 squared. And this is what enables you to actually convert this into 2f1 squares at the same argument, which is what is needed to apply the Clausen identity. Okay? Yes. CFT is entering because I want to identify what 2f1s are in the language of the correlator. So I'm explaining what Ramanujan did. So Ramanujan applied the Clausen identity. What I'm going to do is I'm not going to expand it in terms of the Clausen identity because this is a CFT correlator. I'm going to simply expand it in terms of the conformal blocks. And then I'm going to ask how things converge. Okay? Yeah. No. So the remaining part is also there. I have not simply showed it. Yeah. Yeah. But then, yeah. So here the specific thing is that you have to find an operator that acts on the correlator part of the correlator to produce 1 over pi. So that's the first step. Okay. So it's a very specific correlator. You cannot find an operator that just gives you 1 over pi if you act it on anything, some random thing.
That's a question about functions in general. Like, why was it important? Where was the physical CFT important? Where is the physics of the CFT important?
Yeah. So what I want to do is, the starting point is basically using the Legendre relation. So there is a differential operator acting on a specific combination of 2f1 square, which gives you 1 over pi. Okay. So the next step is a mathematician would expand it in terms of the Clausen identity. Clausen identity is some simple sum. But a CFT person would expand it in terms of the CFT data.
So that differential operator acting on KV1, it's possible, right? You could have some other function. You could take that function also and expand it in conformal.
Yeah, you could do that. Yeah. Yeah, but the point is that you want to converge it. So these are the steps that you would literally produce the usual Ramanujan pi series.
Correct,
Yeah.
I understand. So
Yeah.
I think the block expansion is somehow useful thing to look at.
Yes, that's right. Yeah.
So EFT is only entry in that you're saying functions, then expanded and conformal blocks might be used.
That's right. So because in the Ramanujan thing there was a summation over n. And now, of course, n I have to specify what I mean. So in the Madhava series, there was also a summation over n. In the string theory interpretation, we interpreted that as the string mass level. So here I have to interpret that summation over n in the language of what operators we are summing over. In this particular case, yeah.
Yeah, but I don't think I mean, it's not completely obvious that you would have had like this solo generator giving you.
Yeah, that is also there.
Or something which is just independent of Z and so on. I mean, that's sort of a property of the CFT. I mean, I think that guy, I mean, that says that the correlators obey some null relation or something like that. I mean, I don't know, is that following from that? Is it some null vector type of relation or?
Which one, sorry?
The fact that L2 gives you something simple like that.
Yeah.
Does that follow from some null vector or some condition in the CFT?
I would imagine so. I just have tested it at the level of the equations, but it has to be of this kind, yeah.
Or CFT some relation. That's how.
No. This is a single derivative. So this is actually saying that there is a combination of symmetry transformations, which involve rotations and special conformal transformations that converts this correlator.
No, maybe it's not a null vector because it's global symmetries, but maybe I take that back. Maybe not a null vector, but I don't know what the interpretation is, but it is some global model.
Or you could now reinterpret this as a relation on the correlate.
Yeah.
This particular relation. You could now think.
To impose this as a condition on the correlation function. Is that what saying? Yeah. You could, I guess, yeah.
That condition can be derived from some physical principle.
So it is only for one part of the correlator also, right?
Yeah. So that is a crucial thing, and in fact the story is more intricate because what I'm applying is on the left side and the right side. So the right side actually gives you the same quantity but with a minus sign. Okay. So in order for this to be useful, you should be able to expand this in terms of the conformal data, and in this in terms of the conformal data individually. Only then this becomes useful. And this is only possible because of the log CFT property. Usually that is not possible. So if you just break up pieces of the correlator, each individual piece you cannot expand in terms of the conformal data. Right? Yeah. No, not as far as I know, because I think this is the Legendre relation, for example, the original form of the Legendre relation was very crucial in terms, I mean, it was tied in with the elliptic integrals. And elliptic integrals require sigma equal to half. Yeah.
That you know that when you expand in terms of conformal blocks, you get some positive coefficients.
Yeah. So here you won't have any positive coefficients. No, this is the log CFT. Log CFTs are not unitary. Yeah. Log CFTs are not unitary CFTs. Yes. Sorry. Yeah. Sorry.
Crossing identities is for weapons of the same thing. I mean,
Yes.
you probably need sigma equal to half. You need exactly sigma equal to half.
No, there's a general version with general sigma as well, but it is like a relation of sigma 1 minus sigma, and the second one also has sigma 1 minus sigma. Okay. Now, why this is useful and why exactly? So I think we are getting a little ahead of ourselves because I've not really told you about what we learn or why this is useful to consider from the bootstrap perspective yet. This step is going to be the key player so far as the CFT bootstrap is concerned. Because one way that it could be useful is that if somehow in this relation, when you expand the quantity, this quantity inside here in terms of the conformal data, one could get a situation where only one operator contributed. Okay? Does that make sense to you? So suppose, and that would be like you with just a single operator, you've reproduced the whole thing. Well, I mean, when I'm expanding in terms of the conformal blocks, I meant the global conformal blocks. So not the Virasoro conformal blocks. So I'm expanding in terms of the Virasoro global conformal blocks. So one thing could be that you could ask that, okay, so suppose I take this part of the correlator, and as I said that this part of the correlator and this part of the correlator can be expanded in terms of the conformal data individually. So in particular, to expand this, you just require the log partners of the primary operators to expand this part of the correlator. Okay. And so the question is that, is there some Z or Z bar where only one operator contributes? Okay. Okay. Now, one thing that obviously you can expect is that if you are in the light cone limit, the single light cone limit, then the OP converges, and as a result of which, if you were literally in that light cone limit, then the leading term is going to start dominating. Okay. So that is the kind of thing that you could start asking, that is there some way that all these series formulas could be thought of as some light cone limit, or some version of the light cone limit where only few operators start contributing. So that's the kind of physics question that you would be interested in. And this is where these modular equations play a role. So, okay, so the modular equations, where these modular equations came from, why these are algebraic, they actually need use of theta function identities, which Ramanujan cleverly uses. And I don't know how he solves these. In fact, it's, if you open it and you see surds, square roots within square roots and big numbers and everything, and he solved it on a slate, and I don't even know how he wrote such big formulas on a slate. And so maybe he had many slates or something, but yeah, it's remarkable. And as I said that we wouldn't be proceeding in this language in the CFT perspective, we would actually expand the correlator in terms of the natural quantum numbers of operators in the OPE. So we can work out these external dimensions of operators. And as I said that H1 and H3 are the same, and they work out to be this. So they are negative, manifestly negative if sigma is positive. And H2 and H4 are the same, and they could or may not be negative. And the central charge also gets fixed. It is given by this formula. And if you consider the original Ramanujan series, the choice of sigma that he made maps to these central charges, -2, -7, -25/2, and -24. And these are what are called logarithmic minimal models in the literature. They have been studied. And this C equal to -2 is a famous theory. This is the theory of symplectic fermions, like I said. And this is also a theory that is well studied in the context of the fractional quantum Hall effect. So the place that you might want to learn about logarithmic minimal models is this paper by Zubair and company. So percolation would be C equal to 0. But Michael Floor and his student actually claim that there is some controversy, and the C equal to -24 is rather the appropriate theory for percolation. Yeah. So this C equal to -2 and C equal to -24 have appeared in physics, in discussions of physics. C equal to -7 is discussed, I think, either here on in Michael Floor's review, but not in the context of physics. I've never seen -25/2. I don't know in what context -25/2 appears.
Features that you consider, they correspond to some RNS.
Yes.
In that.
Yeah. So. Yeah.
And why did you choose these values of H's? I mean.
Yeah. So because I wanted the solution to be of this form.
Okay. And that's true only
for those choices. Yeah. 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 So two things before you get lost. Why is a log CFT expected? There is a 2f1 square. The arguments of the 2f1 are the same. So if it comes from a CFT, you have to find a second 2f1 because the differential equation of a CFT has two solutions. The one 2f1 is not going to do. So where is the second? So it's basically taking a degenerate limit. Okay, so a degenerate limit automatically means that there is a second solution. This is where the roots of the indicial equation become the same. And then you need to find a second solution. And typically, when the roots differ by an integer, you get a log times the first solution as the second solution. So this is basically where that comes from. Okay, so a few comments. These are all log CFT. C equal to -2 is a famous one corresponding to the theory of symplectic fermions and contains the physics of critical dense polymers and this nu equal to 5/2 fractional quantum Hall effect. These are not studied, at least in the context of physics, while C equal to -24 appears in the discussion of percolation. The logarithmic nature introduces two sets of partner operators, primaries and the log partners. And it is precisely this that enables us to consider this left part and right part separately, because otherwise this would be a meaningless decomposition. And in fact, these left part and right parts can be considered just in terms of the log partners. And this dispersion relation, this lambda dependent dispersion relation. And using this, we can leverage the Legendre relation. And these different rates of convergence of the Ramanujan series prompts us to expand the rates of convergence of these correlator. Because what you expand the correlator in actually plays a role in how fast you can get a solution or how fast you can you can study a bootstrap related problem. And typically, one is tempted to sort of look at the S-channel OPE, but that is not going to be the fastest. So you require to ask what is the fastest converging representation or what is the fastest converging basis that can be repurposed. And exactly this dispersion relation that I've been using can be repurposed for this purpose. So let me just demonstrate. Let me just tell you what happens. So start off with this Virasoro operator, this curly L operator, act it on this correlation function, and ask how many operators do we need to keep so that we get 1 over pi on the right-hand side. And what we find is that in the large lambda limit, all the non-identity operators correspond to order 1 over lambda, and only the log identity operator survives. And this is the operator that contributes to 1 over pi. So dialing lambda actually controls how much each operator contributes, and this is sort of similar in spirit to the effective field theory story that I said. And it is not trivial. So you would have thought that, okay, maybe this is some kind of a trivial observation, but the kind of integrals that you need to do is something like this. So since you're fond of Olympiad kind of question, you can take it as a homework exercise for yourself. So for any z, you show that this integral is a real integral, d psi 1 to infinity gives you -2. And this is non-trivial because there is a non-trivial z dependence inside here. And it seems like a non-trivial function of z over z. It should all cancel out and give you -2. Yeah, okay. Apart from some, I think z equal to, I forget, I think z equal to 1 is, you have to bypass z equal to 1. Yeah, z equal to 1 and
equal to 0.
Yeah.
It's
Yeah,
like
right.
process that conclude, you will have a pole, right?
Yeah, that's right. So that is why you for z equal to 1, you have, so that does not cancel off with this, so you'll have a pole at z equal to 1. So z equal to 1, you have to bypass.
Yeah,
And I think this one, and z equal to 0 as well, yeah.
You know, 1 and infinity.
Yeah.
Or is it always double? I'm just trying to see if the Z crosses the psi one, right?
Yeah,
Is it double pole so that the...
I think so, yeah.
These formulas, they don't have a delta or z.
What is delta of z? No. No. There is no Dirac delta function. Yeah.
Why would there be Dirac delta function?
So then he would be able to. Yeah. Yeah, no, there are no Dirac delta functions. Yeah, z equal to 1, you have to. Yeah. Yes. Yes. I did check it carefully. Yes. Okay. Yeah, I'm done. Yeah, I'm done here. Yeah. Okay. So, and only the log partner of the identity operator is enough to produce this Legendre identity in the large lambda limit. And this was really surprising to us. This actually says that if you wanted to somehow say, just with this information, start with a bootstrap problem, because we now identified a limit where only one operator contributes. Imagine that we just feed in that information that in this limit only one operator contributes. This would be the correct place to start the bootstrap problem from. Okay. So what is the physics behind the singular moduli? This, unfortunately, it requires a bit more. But then what actually happens is that, as I said, these n's here correspond to, so let's go back to this form. So there is an n here. So Ramanujan actually solves it for bigger and bigger n's, and the modular equations that you get become more and more complicated. So I'll give you a simple modular equation. So the kind of modular equation that you need to solve, I'll write down two of them. So the one of the simpler ones is this kind. And so this actually gives me z as a function of z bar. And what you need to solve is the further condition that this object is equal to 1 minus z bar. Okay, so these are the kind of things that you solve. You find these surd type solutions. And Ramanujan does this by hand in his head or on a slate. So this one, I think the one that I've written there is for n equal to 3. So the biggest thing that Ramanujan notes, this weird function, weird formula that you saw with 99 to the power 4n, that corresponds to n equal to 58. Okay, so Ramanujan solves that one also. And so if you actually look at the analog, so what I'm doing here is that I'm plotting the solution to the first line here. So this will give you a function of z as a function of z bar. So I'm plotting that slice in the z bar z real plane. And the simplest modular equation is for n equal to 1. So that you can easily see that the simplest case is n equal to 1, z naught is going to be a half because the two sides will be equal. And so that red point that you see here is that simplest singular moduli. That is the usual diagonal limit that we consider. This is usually the starting point for the numerical bootstrap program, this point. And the second case, the second modular equation, the singular moduli lies here. And as you keep increasing the order of the modular equation, it gets pushed to the left, which actually corresponds to the point z bar equal to 1 and z equal to 0. Now, those of you who actually know a bit about CFTs, this z bar equal to 1 and z equal to 0 corresponds to what is called the double light cone limit. So you're actually approaching u equal to 0 and v equal to 0 at the same time. If you approach u equal to 0 and v equal to 0 at the same time, this double light cone limit is very subtle because you have to expand the correlators in terms of twist blocks, because the operators with the same twist actually dominate. Okay, and then you would have thought that an infinite number of operators should contribute. But because of this peculiarity of the log CFT, this double light cone limit actually gets converted into a single light cone limit. And that's the only limit that we're interested in. And the single light cone limit is just the usual S-channel OP. And that is the reason why you have the success with just a single operator. And to demonstrate this, you can actually do the same calculation that mathematicians do. So that are the same calculations that Ramanujan would have done in terms of the conformal data. So retain just the first 10 operators. So just the first 10, not in terms of twists, just the first 10 operators that you would get in the power series. And you can actually dial the singular moduli and see how many digits of pi you can capture. And it seems to grow, and this seems to be a logarithmic growth, but some kind of growth. Let's not call it logarithmic, but it seems like it'll just keep growing, which essentially means that if I keep increasing the order, the modular order, I would be able to capture the entire series. So these are my conclusions. I don't really have any conclusions. Let curiosity be the guide. But just to keep you motivated, I'd like to read off this philosophical exchange between Pinky and the Brain. So I don't know how many of you actually have ever watched Pinky and the Brain, but these are two lab mice who are plotting, scheming to take over the world. And so the brain is usually the person who has all these very dangerous schemes or idiotic schemes. The brain says, "Are you pondering what I'm pondering?" Pinky says, "Oh, I have to say the odds of that are terribly slim." The brain says, "True." Pinky says, "I mean, really, when have I ever been pondering what you've been pondering?" The brain says, "To my knowledge, never." Pinky says, "Exactly. Next to nil." So, none of us will be thinking about the same thing. So, I don't know where the questions will lead us, but then I should actually tell you about the contribution of the identity operator from the CFT. It produces this remarkable formula. This is the log identity with Ramanujan's n equal to 58. It actually produces 18 digits of pi, this particular guy. So this is just the contribution from one operator, which you can calculate analytically. So I'll stop there.
That's a general question. Just about first part of your talk about the crossing symmetric. I was wondering whether there's some relation to all this recent work that Emmy and collaborators are doing, where they try to kind of put the SMT channels and everything together in a kind of, I mean, they're going the other way around in some ways. They're starting from various different diagrams and writing it in a stringy way, such that it is, but there they write in terms of some extended Schwinger integral. It's sort of, going in the opposite direction, but I was wondering whether and they have some geometry of,
Yeah, I think that's a great question. I've thought about it. I'm not sure what the answer is, but there was this piece in the dispersion relation which has this kernel times d sigma. So this guy. So it's very tempting to write this as d of log of sigma minus s1, and then there is another piece log of sigma minus s2. So in his story about writing down these formulas, these canonical forms that they consider, they have similar looking objects which involves d of log of s and d of log of t. Yeah, but I don't know a clear connection.
I was wondering whether it's unified parameter space.
Yeah.
I mean, even for field theory also, because they're looking at field theory straight by two.
Yeah. Yeah. Yeah, I don't know. I mean, it's a very good question. Yeah. Thanks. Thank you. Yeah. Thank you. When do we identify something as string theory? Yes, anyway, these people ran away, but if I will develop so within a few months there will be 5 particles.